Hello everyone, let us continue our discussion on reinforced concrete design of circular tanks. We are in 10th week and this is our 4th lecture. So if you recall, in the previous two lectures, we discussed the design of circular tanks with rigid connection between the base and the wall. And we studied two different options. The first one was by carpenter's approach. And then if the carpenter's table are not available, then we can go for approximate options. Today, we are going to learn the design based on IS code method. Now, before we go into the details of IS code method, recall, even in the carpenter's method, we first fix this H by D and H by T. And based on that, we get the two coefficients F and K. Now, here in this IS code method also, it is similar. The only difference is how do we estimate these coefficients. Now, as obvious, in this case also we need to determine the maximum bending moment against which we will design and the maximum hoop tension. Now, in this method we are not going to use the same table that we used for carpenter's method, but IS code provides that coefficients. And for that, we will use the code IS 3370 part 4 will be used for this design, and there we will get the relevant coefficients. We will see the tables in a minute, but these coefficients depend on the ratio h square by dt. So as usual, we will first fix the h, that is the total height. Then based on the capacity, we are going to find out the diameter, and we have an empirical expression for the thickness of the wall. Now, once we fix all this, again, there are two stress components: hydrostatic pressure causing stress on the cantilever walls, which is a triangular load, and then we have the hoop tension, which is directly acting on the wall, but it also varies with the depth of water. So as we come near the surface, hoop tension is less. Now there are different tables. Table 9 to 11 we are going to use for the design. So these tables we will get from IS 3370 part 4. Table 9 gives us the coefficients for tension. Table 10 gives the coefficients for bending moment, and table 11 gives the coefficient for shear force. So once we get these coefficients, we can directly find out the maximum bending moment and other force components, right? So again, here we have the approximate formula. T is equal to 30H plus 60 in millimeter, and the minimum thickness is 150 millimeter as usual. So let us see. So here is the code with the design tables, and then here are the tables. So this is table 9, that is the tension in circular ring walls, and depending upon this factor, you can see here we get the coefficients, and if we multiply that coefficients with omega HR, we get the tension in, notice the unit, kg per meter. Okay, so then table 10 gives us the coefficient for moments, and that coefficient multiplied by omega h square will give us the moment. And here again you see h square by dt is varied, and we get the coefficient for moment. Then finally in the table 11 we have the coefficient for shear. Okay. Now with that, let us see the steps. So we find out the maximum tension, which is the coefficient from the table, times this in kilonewton per meter, then maximum bending moment, which is here, and then maximum shear force. So let us take an example. So we design a tank of 6.8 lakh liters of water. We have a height specified in this case, that is 4.5 meter. The joints are rigid. We use M30 concrete and Fe415 steel. But in this case, we will adopt IS code method for the design. So first we convert this liter into volume and we get the volume as 680 meter cube. Then we get the area of the base and that is 151.11 meter square, and then we can find out the diameter required and it is 13.87, so we can provide 13.9 as the diameter of the water tank. Then we have the sigma CBC as usual, 10 Newton per millimeter square, modular ratio is 13, sigma ST 130 Newton per millimeter square, and based on that three coefficients, K is 0.5, J is 0.833 and R is 2.0833. So we get the approximate thickness of the wall, which is 30 times H plus 50 with a minimum requirement of 150, and then for 4.5 we get thickness of 185 millimeters, so let us provide 190. So T is 190 millimeter, so H square by dt is 7.67. So from table 9, against a ratio of 8, we get the maximum value of hoop tension is 0.575, and which occurs at a depth of 0.6 H, that is 2.7 meter from the top. So maximum value of hoop tension we can now calculate. T is equal to, using this expression, and it is 179.84 kilonewton. Then we go to table 10, and again from there we get the coefficient for the bending moment as 0.0146. So the value of maximum bending moment we get is 13.304 kilonewton meter. Now we can also find out the maximum shear force. As you can see here, the maximum value of shear force, again from table 11 we get the coefficient of 0.174. So the maximum value of shear force is 35.235 kilonewton. So let us first find out the effective depth from the bending moment, and effective depth required is 79.9 millimeter. We have already provided 190 millimeter, so that is sufficient. So if we assume a clear effective cover of 35 millimeter, so then small d is equal to 155 millimeter, which is more than the d required. So AST we can calculate now. Let us provide 16 5 bar. Each bar will have an area of 201 millimeter square. So the spacing for this AST requirement is 793 millimeter square. So for that spacing is 253 millimeter. So let us provide 250 millimeter center to center. Then as usual we design against maximum hoop tension. Recall T is 179.84. So we can calculate AS, which is T by sigma ST. Sigma ST in our problem is 130. So we can calculate the area of steel, which is 1384 millimeter square. Now that we distribute over two faces, so each face will get a steel required as 692 millimeter square. So we can try with 12 5 bars. Each bar is having a area of 113 millimeter square. So the spacing is 163.3. So we can provide 160 millimeter center to center. So AS provided actually is 1412 millimeter square, while the requirement is 1384 millimeter square. So that is okay. Then we have to check for the maximum stress, tensile stress in the composite section. For that again, T, that is the hoop tension, divided by the equivalent area. So that provides sigma CT as 0.869 Newton per millimeter square, which is less than 1.5 Newton per millimeter square, and hence it is safe. Then we have to provide distribution still, and for that again recall we reduce it from 0.3 to 0.2% depending upon the thickness, and in our case we have a requirement of 0.2743%. So the area of the reinforcement is 522 millimeter square, and that again we provide on each face We have two phases, so we distribute this into two phases. So per phase, we have a requirement of 261 millimeter square. So let us provide 8 fibers, and then the spacing requirement is 193.5 millimeter. So we can provide 190 millimeter center to center. Then as we go towards the surface, we can curtail the hoop reinforcement, we can reduce. So that exercise is done here. So for that, again, we refer table 9. So first, at the top, 2.25 meter below the water level. So again, we refer to table 9 and find out the hoop tension coefficient, which is 0.285. And then accordingly, we find out what is the maximum value of hoop tension. And then based on that, we calculate the steel required. In this time, it is 686 millimeter square. And that again, we distribute over the two phase. Per phase, we have a requirement of 343 millimeter square. So 12 fibers will require a spacing of 329.6 millimeter. So we can provide 320 millimeter center to center. So you can see it is here. While below this level, we have a provision of 12 fibers at the rate 160 center to center. Now, we have to design the base slab. For that, let us provide a thickness of 200 millimeter, and the minimum area of steel required is 600 millimeter square. So per phase, we provide 300 millimeter square. So let us try with 10 fibers, and then the requirement of spacing is 260 millimeter center to center. So we can provide 10 phi at the rate 250 center to center. Then again, for this rigid connection at the base, we provide a haunch. So for that, we provide a 150 by 150 haunch, and for that we provide 10 fibers at the rate 200 center to center, and with a freeboard of 150 millimeter above water. So that completes the design. So if we look at the steel, here is the complete detailing, and that shows the steel requirement in walls and slab base, right? So that completes the design of circular tank based on IS code method, right? So go through each and every step, and if you have any doubt, do let us know. We will clear your doubt. Thank you very much.